Welcome to Spelling Bee Ninja, where we embark on a journey through the fascinating world of math. If you're eager to unlock the mysteries of geometry and learn how transformations shape the world around us, you've come to the right place. Join us on this educational adventure as we explore how shapes can slide, rotate, reflect, and resize while maintaining their properties. Subscribe now for free, and let's master math together. Today's lesson focuses on geometric transformations and the captivating ways we can manipulate shapes. Transformations are operations that move, change, or alter shapes while preserving specific properties. This foundational concept is crucial for understanding much of the world around us, from art to architecture, and even science and technology. Geometric transformations include translations, rotations, reflections, and dilations. Let's break down each type and see how they play a role in various fields of study and everyday life. First up is translation. A translation occurs when we slide a shape from one position to another without rotating, flipping, or altering its size. Imagine pushing a book across a table. The book remains in the same orientation, just moves to a different spot. In mathematical terms, every point in the shape moves the same distance in the same direction, described using a vector. For example, a translation of 3:2 moves a shape 3 units to the right and 2 units up. Translations are essential in many areas, including animation, robotics, and navigation. Next, we have rotation, which refers to turning a shape around a fixed point called the center of rotation. Each point of the shape moves along a circular path around this central point. When we perform a rotation, we define it by its center, the angle of rotation, and the direction, which can be either clockwise or counterclockwise. The remarkable property of rotations is that they preserve both distance and shape, meaning the rotated shape is congruent to the original. Common angles of rotation include 90 degrees for a quarter turn and 180 degrees for a half turn. You can find rotations in everyday objects like clocks, wheels, and gears. Reflections involve flipping a shape over a specific line, known as the line of reflection or the mirror line. When we reflect a shape, we produce a mirror image where every point in the shape is the same distance from the mirror line but is located on the opposite side. Reflections maintain distance and shape, resulting in a congruent figure, but they do alter orientation. A simple analogy is looking in a mirror. What you see is a mirrored representation of yourself. Reflections find applications in design, art, and even in understanding how light interacts with surfaces. Now, let's talk about dilations, which change the size of a shape without altering its proportions or shape. A dilation either enlarges or reduces a figure based on a scale factor from a center point. If the scale factor is greater than 1, we enlarge the shape, while a factor between 0 and 1 reduces it. This concept is frequently used in photography, mapmaking, architecture, and model making. For instance, a map is a dilation of reality, utilizing a scale factor to fit large distances onto a small sheet of paper. Speaking of real-world applications, video games heavily utilize geometric transformations. Every time your character moves, jumps, or rotates in a game, transformations are at work behind the scenes. Translations move characters across the screen, rotations change their direction, reflections create mirror effects, and dilations can zoom in or out. These intricate movements are performed in real time, showcasing the power of transformations. The first game to utilize these concepts extensively was Spacewar, in 1962, paving the way for increasingly sophisticated gaming experiences. Designers and artists similarly rely on transformations. They apply translations to repeat patterns, utilize rotations for dynamic layouts, and create symmetry with reflections. Architects use transformations to replicate features like windows and columns, while fashion designers implement transformations to organize patterns. Understanding these concepts enables creators to develop balanced and consistent designs across their work. In line with this, transformations are crucial in scientific fields. Physics uses them to explore how objects move under different forces. In chemistry, they help model the shape changes of molecules. In biology, transformations can illustrate how organisms grow and move. Engineering employs transformations to design intricate structures, and in medicine, they are vital for processing images from techniques like X-rays and MRIs. It's fascinating to see how transformations are universal tools across disciplines, aiding our understanding of the natural and constructed worlds. Another interesting aspect is how transformations can be combined. This combination results in a composition of transformations, meaning we can apply one transformation after another. For example, we could first translate a shape, then rotate it, and finally reflect it. Each step builds on the previous ones, enabling us to achieve complex movements and effects. This compounding of transformations is essential in disciplines such as animation and robotics, where creating lifelike movements often requires a series of transformations performed in sequence. Remember, the order in which you apply the transformations matters, leading to different outcomes. And lastly, let's consider the future of transformations. With technology continually advancing, the role of transformations will only grow. In the realms of virtual and augmented reality, transformations enhance immersive experiences by adjusting what we see according to our movement. In autonomous vehicles, transformations allow cars to determine their position relative to their surroundings. This understanding is crucial for safety and navigation. As technology progresses, our study of transformations will pave the way for enhanced AI, more immersive virtual experiences, and innovations in fields like space exploration. Self-driving cars, for instance, employ transformations to navigate safely through their environment, gathering data through sensors and interpreting their surroundings effectively. As we conclude this lesson on geometric transformations, we've discovered how these mathematical operations, translations, rotations, reflections, and dilations serve as the building blocks of movement in our physical and digital worlds. They are pivotal in artistic expression, scientific inquiry, and technological innovation. By grasping these concepts, we lay the groundwork for understanding more complex systems and applications in the future. It's exciting to think of the possibilities transformations offer in shaping our reality. To recap, geometric transformations allow shapes to move, rotate, reflect, and change size while preserving their core properties. We've explored translations that slide shapes, rotations that pivot them around a fixed point, reflections that create mirror images, and dilations that resize shapes. We also examined the significant roles transformations play in video games, design, science, and technology. As we integrate transformations into various fields, their relevance and utility continue to expand. Understanding these concepts enables us to better interpret our environment, whether in art, architecture, or technological creations. Thank you for joining us on this enlightening journey through geometry transformations on Spelling Bee Ninja. Exploring how shapes and movements intertwine enriches our understanding of the world. Don't forget to subscribe for more free educational content to enhance your learning. Keep in mind, the world is filled with mathematical wonders, and transformations are just one piece of the puzzle. Until next time, keep learning and exploring your mathematical passions.